this nozzle contour design. Coming in from the last 2 weeks, we have a couple of important parameters calculated from CEA based on what we chose for the inputs to the system. So as far as the nozzle is concerned, we have the throat radius and the exit radius designed. This is one of those slides that doesn't matter a ton for actually executing it, but essentially to have an actually ideal nozzle, you don't want any shock waves or pressure compression waves inside the nozzle because those cause losses and slow down your exhaust. They can also rip apart your engine and nozzle, which is not ideal. To do this, the completely accurate way needs to be done numerically with a heavy-duty computer sim, and you calculate the angle change that like the nozzle can take at every given point. So any angle change does create a shock wave, but you want that shock wave to actually be in the same exact direction that the wall is at any given point. Obviously, that's a giant pain to try to do. And when they first came up with rockets in the 1900s, like the bell nozzle type rockets, they just didn't have computers capable of doing that. So what we have instead is a very smart dude at NASA came up with a parabola that gives a good approximation of the curve that comes out of that and get to about 99.8% efficiency. We're going to use that because it's a lot easier and makes a lot more sense. This is essentially the nozzle curve where you have the throat radius down here, RT, and you have your exit radius, RE. And then you can you have a couple different parameters that just kind of guide the curves. You have circles in the actual throat area, like sections of circles, and you have a parabola on the nice diverging straightening section of the nozzle. And here, there's just some terminology that you might hear me use. Upstream of the throat, you have the converging section of the nozzle, which is where the inlet and the chamber are. Then you have the throat. Then you have this right here, which is the diverging section. And within it, this first kind of like curve outwards, this is the expander section. And then the parabola part is called the straightener section, because that's what the flow tends to do in those areas. It expands a lot here, the gas expands. And then the main point of this parabola is to straighten out the flow and make sure that you're not wasting thrust kind of like perpendicular to the rocket and canceling it out. And you want all of your exhaust to go straight out in line with the rocket. So like earlier, a decent amount of this comes with just picking arbitrary numbers. So you pick the starting angle of that parabola and the ending angle of the parabola, and then the length is kind of a function of those. In reality, doing it that way is annoying and iterative. So what we're going to do is we're going to pick a starting angle, make sure that the ending angle is within a certain tolerance, and set a length by multiplying the calculated ideal length by a decimal number, lambda, which is just arbitrary. We're going to validate these later using fluid simulations of each engine. But this is the heavy math part for calculating the length. Once you have that, basically we need to make the parabola and fit it in to actually make this shape here. So over the summer, I wrote a Matlab script and Sam revised it to make it not broken, but it also usually just works to set these constraints in SolidWorks. So we're going to try that first. And if that absolutely breaks SolidWorks, then we can do it with a Matlab script and an equation-driven curve. For reference, here is what the Matlab script looks like. This is for that engine that me and Jackson designed, where I chose a that starting angle of 45 degrees and a arbitrary parameter multiplying the ideal length of 0.1.
Are you in Matlab right now? Because it's still showing the presentation.
Fuck. try it this way then. Matlab. So you get this, where this is kind of the parabola. The scale on this is all kinds of messed up, so ignore that. But this is the parabolic section.
Arun, we have a question in the chat from Rishi. I'm not actually sure what the answer is, so.
That MATLAB script, it uses the same exact method. This is that same equation right there. And then this is just solving for the parabolas equation using a matrix if you have taken linear algebra. You could also solve for just using a system of linear equations. It's just kind of ugly. So then I'll pop and open SolidWorks. Hopefully I still have the engine open from last week. Machining the nozzle is pretty much the same because we use the CNC lathe, so it's computer controlled. So as long as the length isn't, it's really the length that needs to kind of like reach into the nozzle to actually take out material that matters a ton. I really hope I have saved this somewhere. Right. So this is the one we built over the summer, and I'm just going to go ahead and break it all. Okay, so I'm just going to leave the chamber alone for now. Delete everything here. Okay. So this is pretty much the main guide to doing this SolidWorks, because you have your throat radius, you have your, and then the curve coming into the throat on the converging side. The radius on that is 1.5 times your throat radius. So we're going to go ahead. The way I made, actually, not everyone is familiar with SolidWorks. I don't want to do that. I just made this using this arc tool up here, kind of arbitrarily putting this point up there. And now I'm going to dimension this radius here, if it cooperates, which is not. Dimension this, there it is, to be 1.5 times, I have my throat radius in my spreadsheet. Then, so same thing right there. This curve right here is just held because it's a curve that's centered here on this line and is tangent to both the chamber and to this curve here. And that's really all you need to do for that. So now the converging section of this is done. Well, almost done, sorry. The problem is that this is not completely constrained right now. So all you gotta do there is set these two as vertical, and it's gonna break. Don't set those two as vertical. Oh, that's why. My axes are flipped. So I'm gonna set those two, all three of these as horizontal. And going back here, the expander section is kind of defined the same way, where we have it as 0.382 times the throat radius. So I just kind of arbitrarily draw that first. Then same thing, I'm going to set the center point vertical with the other ones, or in this case it's horizontal, sorry. And then dimension that 0.382 times my throat radius. There we go. Now, this doesn't have a defined like length of turn yet, which is fine. So what I'm going to do here is draw a center line, which is just a line for construction off of this. So leave it kind of arbitrary. And I'm going to make it tangent to this curve. And then I'm going to draw.
Hold on, Arun. Does everyone know how to use sketch relations? Did you show them that during the CAD lecture?
Yeah, you select
okay.
them. Yeah.
Okay, cool. Shift select.
And then a second one, which I made, in this case, vertical. It's just kind of a, I'm going to actually rotate my view here so that it makes a little more sense. Assuming I can. Okay, it does not want to rotate nicely. We're staying sideways. And now, so anyway, I'm going to put this in as my, that starting angle, the theta n that we talked about earlier. So I'm just going to choose 45 degrees. So that locks in the length of this. And now for the big fun one, which is the parabola. So within the ellipse tool, there is a parabola option. I'm going to click on that. This one kind of sucks to use. So it's it really sucks to use, honestly. You just kind of start by drawing a random ass parabola. In roughly the right place. Nothing here matters right now because we're going to deal with all of this in a second. Start by rotating that. Oh, Jesus. As I said, parabola tool sucks, but it does work sometimes. We're going to make those 2 points merged. Then we're going to also make these 2 tangent. Now we're starting to look like it's something real. Let's see. So now we can kind of play with this still, but it's overall pretty locked in on the left side of the parabola. We're going to, I'm going to steal this length from my Matlab script because I already had it calculated, but normally you plug in this equation right here with your chosen lambda, and that'll give you your chosen length. Because I didn't do this in the Excel sheet, I do need to grab it from here. I would suggest you do this in the Excel sheet. And this defines the length of just the parabola. Sorry, no, this defines the length of the entire diverging section, so from the throat to the tip of the parabola. So we're going to go find this point, and then out here. So the radii of the circular arcs are from your throat radius as defined by this diagram right here. So the incoming one, the radius is the 1.5 times the throat radius. And then, yeah, perfect. So there we go. We have now defined this parabola's length as well as the starting location and angle. And so the last thing we're going to define, I think, is going to be the exit radius, which for me is right here. We're going to enter that. And it's going to break everything. I'm going to delete that and then figure out why it broke everything. As I said, sometimes SolidWorks does not behave. Let me try to use this tool. So we're going to delete this length parameter for a second and see if it likes it that way. It does. So sometimes your chosen length will result in invalid curves, because what can happen is it'll actually try to invert itself to make that work. Obviously, you don't want that. So instead, I'm going to cycle back over to my Matlab here and see what's going on. Nope, that should be happy. No, I'll just go with a different. And then see what happens. Again, the lambda is kind of arbitrary. It's basically what can you make, how much weight are you willing to carry, and the only good way to characterize how good or how close to ideal you are, even with such a small factor, is by doing numerical sims, which we will get to. Jackson, is next week or the week after?
We can do it next week or the week after. That is flexible. I think we should do it next week.
Fair enough. The parabola is in the ellipse tool in the sketch options up here. It's kind of nasty to work with, but it does. It's easier than doing the map by hand. Now, this should be fully defined, but it's not. And that's why it's not.
Define the exit angle.
Yeah. Which technically should not need to be defined for it to be fully defined, but SolidWorks is weird. So I'm just making another line so I can kind of reference off of it to make that exit angle. And will you let me make an angle? You will not let me make an angle there. So when that happens, you just need to make another tangent line. Yep.
Yeah.
Go that way. For construction, and it's already tangent because I snapped to it when I made it. So we're good there. And now we're going to set the angle between these two. Generally, you want this to be anywhere from like 2 to 15 degrees. The shallower the angle it is, the more conservative you are as far as getting good flow. But also, it adds material and makes the engine wacky. So we're going to say 5 degrees in, it's not going to.
SolidWorks don't like.
SolidWorks does not like a lot of things. 10 degrees. Does not like that either.
Try 15.
Nope.
No. I think you might have just over-constrained it. And SolidWorks is dumb.
Yeah. Yeah. Why are you like this? Nope. I don't like this very
Yeah,
much.
SolidWorks is really dumb. Don't.
Yeah, this is why I usually, when I do this with an equation-driven line, but learning that is much more annoying. So, same exact thing, and now it's happy. We're just gonna go with that. Yeah. So you can see we kind of have everything laid out nicely here. It's not going to make a solid body right now. If I try to leave sketch, it's going to break everything. So I'm going to instead go to offset entities, make a 1 millimeter wall, or sorry, 1 centimeter thick wall. It's going to try to do this. It's going to break everything that way. Right. These two, and try that again. There it is. You can see it's on the wrong side right now, so I'm just going to reverse direction. Yeah, there's a couple ways to make the parabola work, but basically SolidWorks just doesn't like parabolas in general.
Yeah, SolidWorks really doesn't like equation-driven either.
Yeah. Like the regen engine, every time you can't mess with the curve anymore, it'll just break it.
Yeah, yeah.
So I just use offset entities to quickly make a shell. If you don't have to, you can do it manually too. This is just a decent
you can also do a thin revolve.
You
if
can.
you just have that one line, and you do revolve boss, it'll be like sketch is not closed, and then there's an option to do thin revolve, and then you pick the wall thickness, and it automatically will do this. That is one fat nozzle.
It really is. It's a little chubby.
45 degrees is a bit much.
Yeah. But you see as you kind of go through this and mess with the parameters. So for one thing, this has a very kind of high air. Okay, actually, sorry. I did not explain one thing in the map here. So in this equation, this epsilon right there is the area ratio. So epsilon, that's the exit area divided by the throat area. And what you'll see is that number is going to increase for a higher chamber pressure in general. At least that's what you'll get out of CEA. So most of the engines, because this is an arbitrarily high pressure engine, you're going to see much less of a kind of taper here. It'll be a lot closer to a straighter line. But yeah, so I would go with something closer to 30 degrees for your starting angle than the 45 I did here. Mostly because this looks dumb and it's going to cause probably will cause a problem right here when we go to do a fluid sim. But I'm going to leave it like that so we can later go over what the problematic fluid sims look like. And also because I don't really want to fix this right now. So yes, that's essentially the quick and dirty way to make the semi-ideal nozzle curves using the parameters we have. Questions?
Do you want to try opening up the regen engine and showing the curve, the equation? It's not ideal.
I will try.
But it's a way to do it.
Actually,
We have too many files.
I blame you.
It is my fault. Yeah, whichever.
I'm not opening the assembly. Yeah. So for one thing, you can see the regen engine is a lower pressure engine than the one that me and Jackson just sketched up for this. So you see that the it's a lot of more straight line. This is just the nozzle because we have it cut in half for manufacturing purposes. But
hold on, I meant like go to the feature tree and do the like show the actual equation. You have to open up the full non-split engine.
I hate you.
It's fine. It's not an assembly. It's a part. Yeah, full piece. Cannot open. Is that a new? Do you
It
still
got
have
updated.
2019?
I do still have Solder 2019.
All right, I guess we're not going to do that then.
Yep.
Unless you want to transfer it to me.
Yeah, if you want to screen share, we can do that.
Yeah.
While we do this, any questions from anyone? This is messy and it does not cooperate. Like this is probably the step that causes the most pain because SolidWorks is terrible at this kind of thing. And it's a lot of iteration to make basically you just want to make it look somewhat normal and then make sure that the fluid sims look good later.
Can you transfer, make me co-host?
Oops, sorry. I'm also going to
open now.
stop recording.